Chemistry in a nutshell. So what is electrochemistry? So basically the study of how electron movement can allow us to tap into their power to create electricity. Because all electricity is in basic terms is the movement of electrons. So electrochemistry is going to be concerned with how one substance is able to produce electrons, the other substance is able to get electrons. It's a chemical reaction. It's under redox, so oxidation reduction reactions, where if you remember, some element oxidizes and loses electrons. The other element gets reduced and gains those electrons. What we're trying to do with the battery, for example, which is what electrochemistry is going to kind of explain, is we're going to try and tap into those electrons. So before you can go from the oxidized substance to the reduced substance, we're going to tap into that. And that's how we're able to power things. So let's get started. So study how electrons are exchanged between two chemicals. Typically, it's two metals. One gets oxidized and the other gets reduced. And that movement of electrons, what we're going to be analyzing. Movement of electrons can be used in cells that either generate electricity, which are called galvanic cells. They're also called Daniell cells. It's also called voltaic cells. They have a bunch of different names, even called the battery. Don't get too caught up with the wording. The only thing you need to know is the one that's different is electrolytic, and they only have one name, electrolytic cells. These are the ones that require electricity to run. So when do we use this? We're trying to separate ores. So if you're mining, trying to separate gold from silver, from zinc, when they do gold mining, it's not just pure gold they get. They also get other metals as well. And they try to isolate those metals and then sell them. That's how they make profit. So what electrolysis allows you to do is to do that separation process. So we'll come back to that later. All right, so first let's look at oxidation reduction. So oxidation, if you remember, is something becoming more positive, getting oxidized. So first thing you do is figure out the oxidation states of elements. And if you forgot how to do this, you want to go back and look at the oxidation video one more time. So zinc goes to Zn2+, so that's oxidation. It's gaining a positive charge. How is it getting a positive charge? It's losing electrons. So whatever is oxidized is losing the electrons. It's your loser in this contest. And hydrogen is going from a positive 1 charge to a 0 charge. So that's being reduced. It's becoming more negative. I know it's not a negative number, but it's more negative than positive 1. And that's how you want to interpret it. So how does it do it? Well, the only way something becomes more negative is by gaining electrons. So this is reduced. And this is gaining electrons. And those are your two options. Every reaction has something being oxidized and something being reduced. And you want to remember that once you identify oxidation by something, there has to be reduction there as well. There's no way around it. Unless, of course, you're looking at a half cell, which we'll talk about a little later, where you're breaking this reaction into what's called two half reactions. And in the two half reactions, you have the oxidation reaction by itself, reduction reaction by itself. So in that situation, you're not going to see both oxidation and reduction together at the same time because they've been separated out already. All right, so we're going to first talk about balancing reactions. And I should say one more thing about this before we move on. Whatever is oxidized is called your reducing agent. That's a flip-flop of terms because you would think that whatever is being oxidized should be called the oxidizing agent and whatever is reduced it should be the other way, but it's not. And the reason for it is that it's kind of like a travel agent. They are setting up your travel, they're not going with you. Reducing agent sets up reduction, but is not being reduced. So this is the agent that allows reduction. This is what's actually being reduced. This is the agent to allow for that. So that's the last piece of information you can get from this data table. You could figure out the number of electrons exchanged as well, which looks like 2. How can you tell that? Well, if zinc lost 2 electrons, then guess what? Hydrogen had to gain those 2 electrons, and that's where the balancing comes in. And that's the challenging part about this. So you've done balancing with simple reactions. This is not a simple reaction. This is a whole process. And, you know, making sloppy mistakes here is more common, and it's a bigger headache. So chemical equations showing charges of chemicals need not only have elements balanced, but also charges. So here's when you use this. You see a reaction, you see charges within the reaction. Now, typically in a balancing question, you don't see charges. You just see elements, everything is neutral, good to go. When you see charges, you have to do it this way. You could try to wing it and do it the old-fashioned way by just, inspection, putting numbers here, putting numbers here, and see what happens. But trust me, that's not going to be very effective. What you want to do instead is do this. So what is this? So there's two types. There's redox in acidic solution, and there's redox in basic solution. So we're going to go over both. We're going to go over acidic first and then basic. Now, some resources will tell you to do the basic different than what I'm showing you. And it's your call, but the reason I do it the way I do it is because if you do acidic one way, at the end you just do a couple of extra steps and you got your basic solution, you're good to go. So the steps are identical, less chance for errors. If you do it the way most resources show you, it's going to take you a different pathway because you're going to have to treat it like a basic from the beginning and do things differently. I like consistency, I like routines. So I like it when I'm able to do the same thing for both of something and then add something at the end, kind of like doing empirical versus molecular formula. Same principle. We add steps at the end instead of trying to modify in between. But your call. So first thing you need to do is separate the two half reactions and balance them individually. So just like you would think, you balance the elements first and then you go from there. So for each half reaction, this is what you need to do. Balance all the elements except hydrogen and oxygen. So kind of like what we do with balancing equations, we do H and O left. It's just a really interesting situation that you could do that for that and this, and it works out very well. But it does. Just go with it. So that means anything besides H and O, you balance using your usual setup as far as, if there's two coppers on the left, you put two on the right, you balance it. You balance the elements. Balance oxygen using H2O. This is where it gets weird. Because in the back of your mind, like, why can't I just balance O by putting O there? You can't, because sometimes there is an O on the other side. I know, it's really weird, but this don't make you balance the O. So if you have two oxygens on the left, you need to add two waters to the right. And when you do that, you've introduced hydrogen into the mix, right? So you're like, what the heck? This is really getting weird. Don't worry, you're going to fix the hydrogen by adding H plus to the other side. This is why you can't do balancing any other way, because this stuff pops out of nowhere. Balance the charge using electrons. So whatever side is more positive, you add electrons to it. That's how you balance it. Make sure both half reactions have the same number of electrons by multiplying them by the appropriate multiple. What you don't want to see in your final balance reaction is any electrons. If you put an electron in your final balance equation, you screwed up, because electrons should go away. They should cancel out. Add half reactions to subtract identical species on opposite sides of the arrow. So kind of like Hess's law, if you have 3 hydrogens on the left and 6 on the left, you subtract the 3 from the left to make it 0, and you put 3 on the right. Because you're subtracting left from right from left in that situation. Check to see if the elements and charges are balanced. So, shortcut is if the charge is balanced, you probably did it correctly. So if you're pressed for time, you could kind of just rely on that. If the charge is identical on both sides of the arrow, left and right, you probably did it correctly. If you have more time, then you check the elements as well. So let's go over an example, because I'm sure you guys are looking at this and going, what the heck is all this? So there's a couple of different things you could do. You could try to balance this, figure out what the oxidation states of everything is, figure out what's oxidizing, what's reducing, go from there. Or, once again, if you're pressed for time, know that this has to go to this. This has to go to this. Now, why? Ignore oxygen and hydrogen as part of this analysis. What you're focusing on is the other elements. So I need something that has Mn. Oh, this has Mn. Good. I need something that has carbon. Oh, this has carbon. Good. That's the way you want to look at it. Forget the O's, forget the H's, just the unique elements. You're trying to go make a half reaction with just those chemicals. Now you could sit there and forget oxidation states, and then what's the oxidation reaction, what's reduction. I'll do it real quick. So O is -2, that's a -8, that's a +7. So remember the bottom numbers, the ones we care about. Oxygen is -2, -8, that has to be a +8. So this is a +4 because you divide 8 by 2 to get the charge individually, which is +4, which kind of looks like it got hit in there. This side, you're going to +2. So you're going from a 7 to 2. So guess what? That's your reduction reaction. And then this is going from C2O4 to CO2. Well, CO2, we need to figure out the charges. So it's -2, -4, positive 4, positive 4. So now the situation becomes that I did the math incorrectly here because I need to go to -2. So that's where it gets really scary on this stuff because silly mistakes can cost you. This shouldn't be a positive 8 because I ignored the charge. This should be a positive 6. This should be a positive 3. And those are your actual charges. So you could see how easy it is to have a brain fart. Now, this one really impacted our balancing. It would have messed us up if they asked us what were the oxidation states of carbon on the left and right, then we're really messed up. But it's silly mistakes like that that can pop up out of nowhere. So it's a positive 3, now it's a positive 4, so it's going to become more positive. So that's your oxidation reaction. So what does that really tell us? So it could give us a little bit of useful information. If it's reduction, we know that the electrons we're going to be canceling out eventually is going to be on the left side of the arrow. So if we put electrons on the right side for that, we screwed up. We did something wrong. Same thing with this. For oxidation, I should clear that up. So for reduction, electrons are always on the left. And for oxidation, you guessed it, electrons are always on the right. And this is arrows I'm referring to as left as right. Electrons, oops, come on, get out of it. No, backwards. Electrons are on the left. Electrons, are on the right. So for a reduction reaction, you'll see electrons on the left side and oxidation on the right side. And that's a general way you could apply across the board in this section. So whenever you see electrons on the left side of the arrow, assume it's a reduction reaction. Whenever it's on the right side, assume it's oxidation. That's always the case. It will help you, avoid some silly mistakes. It's useful. I mean, nothing else, you get that. But you didn't need to do this. What I did in the first step, I just drawing arrows between the two without figuring out what's oxidation reduction. That was good enough. I could go with that and use that to balance my reaction. So you don't have to do the oxidation states unless they ask you to. But if you want practice, it doesn't hurt. So there's the oxidation states again correctly, because I couldn't do it correctly the first time. So the magnesium goes from 7 to 2, it's reduced, and carbon's 3 to 4, it's oxidized. All right, so we're going to do oxidation half reaction first. So remember, it's going from 3 to 4, right? Not really like it matters. So we're going to balance the carbon first. So how do we balance the carbon? We're going to put a 2 in front of the CO2. Now, when you do that, you've accidentally already balanced the oxygen. That's the only time you could balance the oxygen or hydrogens with coefficients only, without putting H2O and H plus into the mix. Because you balance it, because you're balancing something else. It's more of a consequence than the objective. So in this situation, it's balanced, so I don't need to put any O's on either side, H2O's on any side. But I do need to balance the charge. So you see how you have a -2 charge on the left? That means I need to have a -2 on the right. I can't make this side positive. You can't add electrons and get a positive charge. That's why I added to this side. And remember, for oxidation reaction, which side do we expect it on? You got it on the right side. So there's your 2 electrons on the right side of the arrow, which is what we expect for oxidation. Checks out. You could have also done this half reaction and at the end of it been like, oh, this is my oxidation reaction. So instead of figuring out at the beginning, which really won't matter, unless they ask you for oxidation states, you could figure it out at this stage. And that's another way of approaching this. If you're really looking for what is the oxidation reaction, if you do this, you figure it out very quickly too. So there's different ways to get to the same destination for these. So now you see it's a -2 on the right, -2 on the left. This one's balanced. This is what a half reaction looks like. This is what's going to be considered within your half cell when we get to what galvanic cells are later. All right, reduction. The manganese is balanced. See, it's 1 and 1. We don't care about the charge, right? We do it in order. That's something I want to emphasize. You have to do things in order. So after you balance the elements, then you balance the O's. How many O's? You need 4 on the right. So we're going to add 4 to the right. When you do that, now your H's are messed up because you have none on the left, but you have 8 on the right. So how do you do that? You fix it. You put 8 H's on the left. So now you have 8 H's on the left and you have 8 H's on the right. You're good. Oxygen is balanced. Everything is balanced. Your elements are balanced, but the charge is not. This is where it gets kind of rough because here's where your objective is. But guess what people do? Here's the most common mistakes in this question. Ignoring this, so not realizing that overall it's a +7, or trying to go straight to 0. ignoring this positive 2 and be like, oh, okay, what's going to add? Let's say you forgot it was positive 7. You should just say, okay, I'm going to add 7 electrons on this side, and that's it. I'm good. No. You're trying to go to 2, positive 2. You're not trying to go to 0. So don't assume you're going to 0. Look at the charges, and if you're not in the habit of writing charges, you're going to get nailed in this section, so be careful. So how many electrons do I need to add to get to positive 2? 5. Because 5 plus 7, negative 5 plus 7 gives me the positive 2 that I'm looking for. That's what I'm going to do. Add 5. So this is another balanced half reaction now. So you have 5 electrons on the left, and on the other one, if you remember, you had 2, right? So now you're going to have to fix that. You're going to have to make the electrons the same, but we'll get to that in a second. The key thing here, this is what we refer to as your reduction half reaction. Why it's reduction? Where are your electrons at? Left side. That's why it's your reduction half reaction. So combine the half reactions. So at this step, you need to put them on top of each other. And I know this looks like it's a lot of work. And honestly, until it becomes automated in your head, it is a lot of work. But once it gets automated, one less thing you have to worry about. So now you look at it, you realize you have 5 and 2. That's not going to cancel no matter what you do. You can't have 3 electrons floating if you're thinking that. So what I need to do is multiply the top reaction by 5, everything by 5. And a bottom reaction by 2, everything by 2. Why? Because I need to get rid of those electrons, but when I multiply by a coefficient, it has to be across the board. It can't just be selective. And that's what I'm going to do. So when I do that, I get this. At this step, you can get rid of electrons. And that's the only point of doing that multiplication to begin with. So very similar to Hess's law, right? The whole idea of you trying to cancel things out, make sure the numbers are correct. The only difference is for Hess's law, you have a final reaction already. You know what you're shooting for. Here, you have no idea. You're trying to figure it out. So then we add these together. We get this. And now what we're going to do is get rid of those electrons. Now, you could have just canceled it here, and that's probably the best route. Less things to look at. So 10 electrons here, 10 electrons here. Anything else that could cancel doesn't look like it, so everything else stays. So when you do it, you end up getting this. What's on the bottom? That's a balanced reaction. Now, if you think you could balance this by inspection, figuring out those values, then good luck. It's too much work. This looks like a lot of work, but at least you have a system. And the system leads you to the correct answer every time. If you try to do it by inspection, you're going to screw up. And you give yourself a headache. This will take you 20 minutes if you're lucky to get this on your own. But, it's your call. Less work, more work. So this is an acidic solution. All right, let's look at basic solutions. So like I said, my system's a little different than what you're going to see in the book and other sources. But I think it makes more sense. So the first 4 steps, still the same. Well, we just saw, do the same exact thing. Don't change anything there. Everything, even the last step. Pretend like you're bouncing an acidic reaction. Get to the destination, and at that point, you're going to make a couple of adjustments. So once you have what you saw in the previous question, you're going to add the same number of OHs to H pluses to both sides of the arrow. So if you look at this, you see I have 16 H pluses on over here. And that's it, right? So what I'm going to do is add 16 OHs to this side. I'm going to add 16 OHs to this side as well. It's got to be the same number for both sides. Otherwise, your balance equation would just become unbalanced. That would suck. What you're going to do now is make these two turn into H2Os. 16 H2Os, because H plus OH minus produces H2O. And this side, you'd have 16 OHs. You don't really do anything with it. So the last thing you need to do, and this is why the system's a little easier, you have 16 on this side, you have 8 on this side, these 8 go bye-bye, this becomes 8, and you're done. You're just balancing basic reaction. See how much easier that is? I mean, all you're doing is an extra step at the end. So if they say basic solution is the same system at the end, you look at your H's, oh, I have 16. Okay, add 16 OHs to both sides, cool. Change this H2O, cancel H2O on opposite sides. We're done. That is what it looks like for basic solution. It sounds kind of scary, but that's all you're really doing. That's why the system works better. So that's how you would balance it. So let's take a look at one in basic solution. So your reduction is that. Once again, you don't need to really figure this out ahead of time, but if you want to, it doesn't hurt. And there's your balancing of the oxygen. So I put two H2Os on the right. Why? I have two already. Don't forget, you could have O's already. Don't ignore them. Don't just put 4H2O because like, oh, there's 4. Use your head, guys. Most of chemistry is just logic and paying attention to details. So don't forget that. So 4 H's on the right now. I need to fix that on the left. So there's my 4 H's. Balanced charges, adding 3 electrons. Why 3? There's your little best friend, the little negative charge that most people ignore, because most students will put 4 on this and that the whole thing is screwed up. Imagine doing all that work and having one little brain fart cost you the points. Sucks. That's what ends up happening. All right, so for oxidation, same thing. You balance your O's. You have one H2 on the right, so you have one O on the right, so you put one H2 on the left to balance it. Now your H plus are messed up, so you need to put 2 H pluses on the right. Now your charge. Don't forget, -1, +2, -1. You're shooting for -1. So how do you get to -1? You add 2 electrons to this side, because the 2 electrons get rid of the positive charge from H and leave just a -1, which is what you're shooting for. So that's what it looks like. Now to combine the reactions, and at this point, you need to multiply the top by 2, the bottom by 3. You're looking for a common multiple. For those wondering, how do I get these values? Find a common multiple for 2 and 3, for 2 and 5, whatever it is. If this was 6 and 2, I just multiply the bottom by 3 and I'm done. You know, that's as simple as that. It's when they don't have a common, you can't divide one to the other that it becomes more entertaining. So balance the charges. So after you combine the reactions, you balance the charges, multiply the top one by 2, bottom one by 3, you get this. So at this point, you should be looking at it and saying, oh, okay, get rid of the electrons, wonderful. I could get rid of all these hydrogens and have 2 left on this side. Remember, it's subtraction. That's what you're really doing. H2, I could get rid of all these, leave one over here. Nothing else cancels, and there's your reaction. So when you do all that, you get this. So now what do you do? Well, remember, it's basic solution, so we're going to add OHs. We're going to add 2 on the left and 2 on the right. Convert the H plus and OH to H2O. And then as a last step, there's 1 H2 on the right, 2 on the left. Get rid of the one on the right. Make it 1 on the left, and you are officially done. So that's how you would balance this reaction. So you notice, same exact step as acidic. You just add a couple of steps at the end, you call it a day. I think it's a lot easier, but your call. I provide you the simplest route, but I know some of you guys like to go on long, convoluted journeys. So, you know, you're calling which journey you want to take. All right, so the whole point of balancing reactions is because you need that to do galvanic cells. Now, the good news is when you're doing galvanic cell balance reactions, a whole lot easier. Way, way easier. The numbers are more manageable. You don't get any scary chemicals typically. It takes you a few minutes at best. Wonderful situation. So why did I show you the long way or the harder ones? Because they pop up as well. Depends on the generosity of the AP board. Sometimes they'll give you a scary one just to throw it in there. And if they give you one of those, it's 1 point. I know what you're saying, but 1 point is still 1 point. And if you could get that 1 point, it helps you. Also known as voltaic cells, they produce energy through oxidation reduction, which is what we just looked at. So basically, those electrons the previous reaction produced, which in this case was what? A total of 6 electrons being produced, the 2 times 3. The numbers of electrons you canceled, that's what you're going to tap into to run the battery. Composed of an anode compartment where oxidation occurs and a cathode. So now we're going to get to some terminology. So remember we said oxidation. What we know so far about oxidation, electrons on the product side. It's the one that becomes more positive, right? Now we're going to add one more piece of information to that. That's also your anode. Your anode is where oxidation occurs. Your cathode, that's where you have electrons on the product side. That's the one that becomes more negative. And here's the other piece of information. That's your cathode. So yes, you have to synthesize all that information together. So when you hear oxidation, all those things need to be popping up in your head. It's, electrons on the product side. It's the anode. It's the one that produces electrons, and it's the one that becomes more positively charged. All that's to flow in your head. You're going to have a table of reduction potentials, which is in the back of your outlines you can use, and back of any reference table for electrochem. It gives you voltages for everything. That's what it looks like. So you'll see this in the back of your textbooks or your outlines, whatever you're using. So 2.87, 1.7, that's the volts. So if you've all heard of volts, right? So this is how many volts of energy this can produce. So a 9-volt battery can function with about 3 of these. This is not what 9-volt batteries are made of, but the point is they hook them up in series. So a 1.5 volt battery could be made of 5.3 volt cells. So what they do, they create these individual cells, and then each cell produces that certain voltage, and then they put them in series, which means they hook them all together so that your overall voltage is the addition of each one individually. That's what in series means. So that's how they make, 1.5 volts, your little AA, AAA things. 9 volts would be like, obviously more cells. Even a car battery, an electric car battery, or even a combustion car battery. So if you're looking at electric vehicles, it's not just one big slab of, metal doing the reacting. It's a bunch of cells. Each of those has multiple cells, and that's what produces the electricity that you're shooting for. The thing you want to notice, these are all reduction. This is called the reduction table, standard reduction potential table. All of them have electrons on the left side. And as you know, redox requires reduction and oxidation. So what you're going to end up having to do to get the voltage for a cell is flip one. One of them has to have electrons on the product side, the other on the reactant side. This will make more sense when we start going with some examples. But just be aware, this only gives you reduction potentials, nothing else. And these are your voltages associated with them. So you can see some of these are unfavorable, like lithium. Does it want to get reduced? Heck no. That's a very negative. The more negative, the more non-spontaneous it is. So remember spontaneity from free energy, your old friend? Guess what? It's back. It goes in this formula here. So here's your new free energy formula we'll be talking about later. So it's the negative of the moles of electrons. Those electrons you cancel down the balance reaction. That's what your N is. Faraday's constant, which is 96,500. Gigantic number. It's not volts. Let's put 96,500. Forget the units for now. And then E, which is your voltage. So when you multiply all these together, you get the free energy. Here's the cool thing that you have to pay attention to. You see how there's a negative in the front? That means that any time your voltage is positive, these numbers can't be negative. Electrons, I know what you're saying, they're negative electrons. No. The number of electrons, not the charge on them. Ignore that. So this is a positive number, this is a positive number. This can be either positive or negative. This is the one that counts. When your voltage is positive, guess what your G will always be? Negative. And what do we want for spontaneity? Negative G. So any of these voltages that are positive, they want to happen. The ones that are negative don't, because if you plug in a negative into this equation, you get a positive change in G. That's a bad thing. Your free energy is positive. We don't want that. So that's why these reactions in the bottom really don't want to happen. So you ask yourself, then why the hell are they there? Here's why. These are the ones that want to get oxidized. These are the ones that you would, when you flip them, because when you flip this reaction, here's the cool thing, kind of like Hess's law again, this becomes positive. So you flip the sign. The only difference between this and Hess's law, and this is what I want to make clear, is let's say you have to multiply this by 2 to make the electrons match up for your cancellation. The 2 does not ever go to the voltage. So with Hess's law, you'd multiply the enthalpy by your coefficient 2. For this, for voltages, you cannot do that. No. Big no. Can't do it. So be aware of that. You cannot multiply the voltage by that value. It's not going to work. All right, so let's go through this. Shows voltages that results when an element undergoes reduction reactions. These are all reduction reactions, so all of them have electrons on the reactant side. That's how you can tell. The higher it is in the chart, the more it prefers reduction. So if they're asking which one of these ones get reduced the most, chlorine, no competition, none whatsoever. Which one of these ones get reduced the least? Lithium, no competition because the voltage is negative. This is very positive. So you could figure out what really wants to get oxidized and reduced based on the voltage value. That's about the only way, other than this placement on the table. The higher up it is on, let's say there's no numbers, just by looking at the placement, you could tell what wants to get reduced the most, whatever's higher up. So let's say you're comparing O2 versus Fe, which one of these wants to get reduced the most? You say O2 because it's higher up in the table. You don't have to look at the voltage; it's just higher up. Which one of these wants to get oxidized the most? Fe, no doubt, because it does not like reduction compared to the O2. So if you're comparing two chemicals, just look at where they are in the table. The higher up they are, the more they want to be reduced. The lower they are, the more they want to be oxidized. So lithium wants to get oxidized the most. Fluorine wants to get oxidized the least, just by placement. So this table is very useful, and you'll be using it for a lot of questions, so get familiar with it. Negative voltage indicates that the reaction does not want to occur. So, like I said, those ones below hydrogen. Hydrogen is your reference point, by the way, for those wondering. That's your 0 point. So we consider that voltage 0. So they react all of these against hydrogen, and that's how they got these numbers. So they compare it against hydrogen. That's your 0 standard. All right, so anode and cathode. So there's a lot going on in this picture, and I know you're looking like, oh my God, what the heck is all this? All right, so how do we know this is the anode? There's different information that they'll give you. They'll identify your anode. So let's say they give you a balance reaction. Let's say it's the balance reaction for this. This is for this. Obviously, the zinc has to be our anode because the electrons are on the product side. You could also figure out based on voltage. There's different ways you can figure out your anode and cathode is. The main thing you want to know is an ox rides a red cat. Kind of like, or I guess that's a little scarier when you think of it, an ox riding a red cat than a red cat riding an ox. Ordinarily, I would say, Puss in Boots riding an ox, but this is more dramatic. You're probably more likely to visualize an ox riding a cat and go, what the? It's those what the ones you're going to remember, right? The weirder it is, the more likely you can remember it. So we're going to go with ox riding a red cat just for fun. So in this situation, that's going to be considered your oxidation is always your anode and your cathode is always reduction. So this is a quick little mnemonic to remember this. All right, so let's get to this. So this is your anode. So your anode is where electrons are produced. So electrons will always go from the anode to cathode. Now, you may think the anode's always on the left, cathode's on the right, because you're going to see it a lot that way. Don't do that. Base it on the information. Sometimes they'll put the anode on the right to mess with you, and sometimes they put it on the left. There's no location-specific situation. It's not normal procedure that anode always has to go on left. In fact, people used to always think that, and of course the AP and their wisdom said, okay, we'll give you a question that contradicts it. Sure enough, they put an anode on the right, and I think the average out of 10 points for that was like a 3. So, it's very easy to misunderstand things. Don't go left and right. Base it on the data, base it on the information. I'll show you exactly how to identify the anode and cathode, by the way, so don't worry about it. So this is your anode. Your cathode is where reduction occurs. So what that means is that the anode is making zinc into Zn2+. You can see that. So over time, you're going to produce more and more zinc 2+, right? That's the whole point of this reaction, Zn2+ and 2 electrons. The 2 electrons go through the wire, do this, and the switch, by the way, a common thing, they'll have the switch open, and they'll ask you, okay, why doesn't it work? Because the switch is open. The switch has to be closed for these electrons to go from here to here. Here's a voltmeter to measure voltage, just 1.1 volts. That's how much this reaction produces. And then it goes to here. That's where the electron travels. But let's go back to this. So Zn2+ being produced. So do you notice over time, you're producing more and more positive charge? Originally, look at your overall charge. It's 0. Look over here. Overall charge, 0. +2 and -2. That's not accidental, guys. If you're going to build a cell, you have to make sure overall charge is 0. Sometimes you'll get multiple ions floating in there. You have to make sure it's 0. So your number of ions depends on whatever gives you a charge of 0. That's a very big deal. And conceptual is very important. I'll show you why in a second. So as I was saying, you produce more Zn2+. So you're no longer 0, right? That's a very bad thing. Your battery's going to be dead. Simple as that. If your charge on each side is not net zero, your battery is going to die. It can't function in an imbalance of charge. So how do you fix that? That's the whole point of a salt bridge. That's what this thing is. What the salt bridge allows you to do, it allows you to balance the charges. So what does that mean? So you see on this side, you're producing more and more positive 2 charge. Each time you produce one Zn2 plus, 2 nitrates come in here. Why? Because one Zn2 plus and 2 nitrates gives us a charge of 0. So if they ask you, what's the point of a salt bridge? To balance the charge in the individual compartments. That's the whole point of a salt bridge. So you want a salt bridge, or you want chemicals in a salt bridge that allows you to do that. Now, you also want to pick something that's not reactive. That's the fun thing about this. Because here's the thing. Let's say you said, instead of sodium nitrate, you made a mistake. You said, you know what, I'm going to use NaOH. Why not, you know? So the OH floats in here instead of the Na+. So you're like, so what? What does that matter? Zn 2 plus OH minus, we could balance it as we go, produces a precipitate. Very bad. Your battery just died again. So not only do you have to consider using a salt bridge that actually has a positive and negative ion, you also have to make sure that it does not form a precipitate with anything in either compartment. So yes, your old friend solubility rules are back in play. That's the reason you have to memorize them. Like I always tell you in the beginning, right? If I make you memorize them, there's a really good reason. That was a good reason. So in this situation, the salt bridge, the only objective here is to make sure that the charges stay balanced and it does not react with anything in the compartment. So if they give you choices for salt bridges, what they're really asking you is, okay, which one of these is not going to react with anything in the compartment? That's how you pick it. They also want to mess with you sometimes. Sometimes they'll say, you know what, can CDS be in the salt bridge? Now, for those that are really, savants at the net ionic stuff and solubility, you're like, heck no, that's insoluble. How can you produce a salt bridge, which is supposed to have ions, with a solid? That's impossible. You're absolutely right. For those that are like, oh, yeah, you may want to go back and review. So that's where you want to take this. So that's how you identify your salt bridge, and that's the point of a salt bridge. So on this side, what happens is that these copper 2 pluses take those 2 electrons and they plate themselves on top of the original copper. So you get more and more copper on here. Wonderful, right? But you also lose a positive charge, positive 2. So what happens each time you make one of these into a solid copper? And this is the reaction, right? There's your solid copper, in case you're wondering where it came from. You add 2 NAs to take the place of the copper. Same logic. Your charge has to be 0. That's the only objective. The other thing you want to pay attention to is that logically, you expect the mass of this to decrease over time, and that's absolutely true. The mass of your anode will always get smaller over time. That's another detail they can give you. Like they don't say with the anode and cathodes, they say, okay, one with zinc got smaller mass-wise over time. You're like, oh, that's my anode. Perfect. That's always the case. Or they'll tell you the one that has the copper started having a brown substance plate on top of it, or the mass increases. That is always your cathode. So your anode mass goes down, and your cathode mass goes up. And that's always the case. So oxidation occurs at the anode, which leads to the mass of electrode getting smaller due to solid metal changing. And there's your cathode, which is the mass is getting larger due to that. So these are all details you can gather from the information provided. And together, that will give you a big picture of what the heck is going on. So you do need to pay attention to each of those details. Then as a cell operates, the net charge in each compartment needs to be 0. We already talked about that. There's a built-up of a positive charge in the anode due to solid zinc becoming zinc ions. And then more zinc plus the nitrate is there, so you have to balance that out by adding more nitrates. So these are all stuff we talked about. And then, of course, you have the other parts, which is the buildup of negative charge in the cathode due to copper cations changing to solid copper. So how do you balance that out? By adding more sodium. So these are all the different features of the cell that you need to pay attention to. Salt bridge, we talked about it. What's the whole point of it? Make sure it doesn't react to anything in either compartment, and also make sure the charge stays balanced. the reacting with each compartment is something you have to keep in your head. You don't write that as part of your answers or explanations. But the whole part about making sure that it functions to balance the charge in each compartment so they stay as a net charge of 0, that is important. And that's how you would justify the purpose of a salt bridge. Its only functionality really is to balance the charges so that the charge in each compartment stays at 0. So if it doesn't stay at 0, then you have a problem. Anions go to the anode, cations go to the cathode. So for the salt bridge, for those of you like, how do you remember what goes where? A to A, C to C. So what does that mean? Anions to the anode, cations to the cathode. Easy to remember it. All right, reactions of the anode. Metals get oxidized, producing a metal ion and electrons. So the mass of it decreases. Metal ions go in the solution, reason why the mass of electrode decreases while the electrons travel through the wire. And here's the other thing that people have a brain fart in. Electrons go through the wire, ions go into the solution. So they're asking you, what happens to the zinc ions that's produced here? For some reason, I don't know why, students think that it goes to the wire to the other side. No. None of that's silliness, guys. The zinc goes into the solution. So if you actually sit there after this reaction is done, you could isolate your zinc back together. You could do two different ways. You could add a chemical that forces zinc to become a solid, or you could drain off all the water and then zinc will form precipitate with whatever's left, the anion left in there. Either way, you could isolate these ions after the fact. That's very simple. But please remember, the mass that's lost here goes into the solution. It doesn't go through the wire. The only thing that could travel through the wire is electrons, and that's it. That's as far as we go from it. And here's the reaction that occurs at the cathode, in case you guys are wondering. Copper 2+ in solution. So you want to have a metal in your cathode compartment that's the same as the ion. So if you have copper here, you want to have copper ions. You don't have silver ions. But silver on top of zinc creates an impurity, because now you have silver and copper together. That's not going to work. So when you're picking your solutions and you're picking your electrodes, like if I know that I want to use copper as my electrode, I want to make copper nitrate my solution. Why? Because you don't get an impurity out of it. That's the other thing you want to pay attention to. You want to make sure that the metal used in the solution is the same as the one that matches your electrodes. These are called electrodes, by the way. I should have pointed that out earlier. So these pieces of metal are called electrodes. Electrodes, this and this are both electrodes. All right, important aspects of galvanic cell. The movement of electrons from the anode to cathode create voltage. This is called EMF. I know it's a lot of semantics. They have 5 different words for every concept in this section. God knows why. So EMF and voltage are synonymous. It can be used to drive things like light bulbs and toys. In order to be galvanic cell, the sum of the reduction potentials must be positive. In English, that means when you add your two half cells together and add the voltages together, they will be a positive number. Electrons flow through the wire, not through the solution, through the wire only. What if you don't have a wire? Your battery is dead. You need the bloody wire. Ions flow from the salt bridge with cations going to the cation. Cathode. Cations go to the cations. I'm not really correct. It should be going to the cathode. And anions going to the anode to keep the net charge at 0. Important aspect of the compartments in order to use standard reduction potential. So we know that this little circle represents standard conditions, right? So that's 25 degrees Celsius. That's 1 atmosphere. And that's 1 molar. So that's standard conditions. So this 1 molar is the new member of this party. So all these voltages we saw are based on the concentration being 1 molar. What if it's not? We'll come back to that a little later. Electrons flow through the wire, connecting the anode to the cathode, and ions flow from the salt bridge, but cations go to the cathode and anions going to the anode. So we've talked about all this, but it's just reiterating that. Electrode compartments where oxidation occurs, that's an ox, and remember red cat. Just remember an ox riding a red cat. That's how you can remember anode is always oxidation, cathode is always reduction. All right, so here's your chart of voltages, and this is a lot more detailed than one you saw earlier because it's got more chemicals. So which one of these ones get reduced the most? This one. What ones get oxidized the most? This one. So if I were to do a reaction between those two, this would be my reduction reaction. This would be my oxidation reaction. Because when I flip this, I get a positive voltage. And then 3 plus 2.87 gives me a very, very high voltage. But you already know that the most common battery is lithium ion, especially for the high efficiency ones. So they actually use a combination of lithium for those batteries. We don't use fluorine. Fluorine can be problematic. It's fluorine ion, fluoride, I should call it. It's not a chemical that we want to have for everyday purposes. And we don't want a gas being produced or have a compressed gas as part of a reaction. There's more safety concerns to deal with. All right, reduction potentials, voltage associated with a chemical being reduced, given on a constant table. We just saw those. Those are all reduction potentials, right? Reactions of voltages can be flipped to give you oxidation reactions. So if you want oxidation, just flip those reactions. So basically, in any scenario, you're going to have one of those written as is, reduction, and then you're going to flip the second one to make it oxidation. Because what do we always need in a galvanic cell, or what do we always need in redox? We need reduction and oxidation. So something's always going to have to get flipped. Way to help distinguish oxidation from reduction is if electrons are on the product side, it's oxidation. If it's on the reaction side, it's reduction. That's what we talked about earlier, right? Oxidation, electrons on the product side, reduction on the reactant side. So here's an example. So as written, this reaction does not want to occur, right? Because your voltage is negative. And we established that negative voltage means non-spontaneous. So how do we make it spontaneous? We change it to an oxidation reaction, and voila, now the reaction really wants to occur, oxidation. The larger the potential for a half reaction, the more positive it is, the more likely the reactions to occur. So it goes back to the whole voltage thing, right? Fluorine really wants to get reduced because it has a very high voltage. So the more positive the voltage, the more it wants to occur. That's what this is telling you. So here's your example with fluorine. This really wants to happen. This is really, like, it does not want fluoride to become fluorine gas. It's really hard to make fluorine gas out of fluoride. Almost impossible. But you could go the other way pretty easily. Fluorine has a very large reduction potential, so it's likely to gain electrons and be reduced. So just remember, the bigger the positive value for the voltage, the more that thing wants to occur. So let's take a look at a scenario, see if we understand this stuff. So what's being oxidized here? Not much information, except, they gave me the anode. So that's how we know what's being oxidized. So this is what's being oxidized. The zinc is being oxidized. They're going to ask for identity of the substance. It's not zinc ion that's being oxidized. It's Zn being oxidized. Please make sure you understand the difference. Zn2 plus cannot become more positive. It's impossible. Zn can. Which such is going to increase in mass? The cathode, right? It's always the case. The cathode always increases in mass. In which direction do electrons flow? Always from anode to cathode. Always. All right, so now let's get to voltage calculations. You calculate by adding up the voltage for oxidation reduction reaction with the voltage for a reduction reaction. So calculating potential for redox reactions, which is the same thing as saying calculating the voltage. One of the reactions needs to be flipped. Now, they may mess with you sometimes and give you an oxidation reaction already flipped just to see if you understand that if your electrons didn't cancel, you screwed up somewhere. Just in the back of your mind, always remember that electrons must cancel. Electrons must cancel. So that's how you can catch brain farts. If you're adding electrons instead of canceling them, you messed up somewhere. This number of electrons lost must equal the number gained. The half fractions must be multiplied by integers to balance them, but we don't multiply the voltage. So in English, what this is telling you is that multiply whatever number makes the electrons equal for both half reactions, like what we did with balancing, right? If the number is not a whole number, you screwed up somewhere. But you don't ever multiply the reactions, like whatever number you multiply more reactions, you don't do that to the voltage. Voltages cannot be impacted at all. They're constant values. You can't do like enthalpy and say, oh, I have 3 moles of this, so I should have 3 times the amount of voltage. No. That's the one separation between it and Hess's law. Everything else in this scenario is similar to Hess's law, except that. So be aware. If the voltage is negative, then the reaction is an electrolytic cell and needs energy to operate, while positive voltage indicates it produces electricity. So you're going for positive numbers. And why? Because the whole NFE formula, right? You want a negative G. Some examples of this. So give a balanced reaction and voltage for the following redox reaction that occurs in a galvanic cell. So here you could tell what's being oxidized and reduced really quickly. You can see it's a lot easier to do this for this kind of scenario because there's not a whole bunch of complications. 0 to positive 2, that's oxidation. 3 to 2, that's reduction. More positive, more negative, right? That's all you're shooting for. So here's our two half cells. We look at it and we ask ourselves, okay, I need to flip one, right? Because the electrons right now are on the same side. I can't have them on the same side. I need to cancel them out. So which one do I flip? Well, whichever one gives me a highest positive voltage. If I flip this one, my number becomes larger, stays positive. Whereas if I flip the top one, my number becomes negative. And that's what I'm trying to avoid. So what I'm going to do is reverse reaction 2. So I can get my electrons on opposite sides. Then we're going to balance it. So how do I balance it? Well, you have 2 electrons on this one, so you need to have 2 on this one. So you're going to multiply everything here by 2. I don't multiply the voltage by 2. Be careful with that. It's Lycas's law until that part. At this part, you don't multiply through like you would enthalpy. Your coefficient or whatever you're multiplying by stops here. You can't go past that line. Voltage is not affected by it. So then we put the 2 half fractions on top of each other and cancel. Notice there's 2 electrons on the left. You have 2 on the right. They go away. And that's what they have to do always. Your electrons have to go away. Otherwise, you're screwed up. And this is your N in that formula, change in G equals negative NFE. That's your N. The number of electrons you just got rid of. Just a little side note. All right, our voltage is positive, 0.34 volts, 0.3 volts. So we know we did it correctly because we got a positive voltage still. If we had a negative here, you made a boo-boo. Because a galvanic cell, you can't have a negative value for a galvanic cell. Now, I do want to be clear. If all your data points to electrolytic cell, that's where you're supposed to go. So don't try to manipulate the question of galvanic cell unless they tell you it's a galvanic cell. If they didn't tell you what it is, don't assume. Because in the last few exams, they messed with people where it was electrolytic cell, which is one where the voltage is actually negative, and people were trying to force galvanic on it. So look at your data. Let it guide you. Don't assume things. If they tell you galvanic, that's keyword for, okay, positive voltage. That's the way you want to associate it. So there's your balanced reaction. All right, we're going to try another one. This one we're going to do is one where we're going to build the cell afterwards. So I'm giving you choice for salt bridge. I'm giving you reactions. And your job is to figure out what the heck is my scenarios. So before I even start, because I have a balanced final reaction, I can figure out what my anode and cathode are in seconds. So this is your anode. Reductions, that's your cathode. This is oxidation. So you can figure that out if you have a balanced reaction within seconds. Now, typically they're not going to give that to you, so you're not going to have that opportunity. You have to base it on this. But even if you base it on the voltages, which one are you going to flip? That's right, the bottom one. Why? Positive voltage. If you do the top one, your voltage is still negative. That's not what we're shooting for. How do we know it? Because it's occurring in a galvanic cell. Once they tell you that, that's keywords for, okay, positive voltage. That's the way you want to make the connection. So here's my setup. Here's my voltage. So I got 2.37, 1.66. When I add them together, let me go back one. So this is what you're looking at right there. So electrons go away. So my voltage is positive. We're good to go. There's my anode. Magnesium is my anode. Aluminum is your cathode. So we're going to build the cell real quick, just so you can see how the information can now take you somewhere else. So what I'm going to do is I'm going to put the anode on the left, on the right, and put the cathode on the left, just to show you that it's not side specific, so don't make the mistake. Put your electrodes, 2 pieces of metal, your electrodes, right? Connect them with a wire. Put a salt bridge. We don't know what chemical yet. We'll come back to that. All right, so we said that your anode is magnesium, right? And the reason we know that is because the one we flipped, right? The one that gives us the positive voltage. And if you remember in the original overall reaction, which is down here, it went from 0 to 2, so that's your oxidation. So anyway you flip it, it's your magnesium. So I'm going to put magnesium here. So if I have magnesium here and it's oxidation, that means Mg2 plus should be floating in solution, right? Because what's going to happen, Mg is going to break apart and produce Mg2 plus. So the mass of this is going to decrease over time, right? That's one piece of information we can gather. It's not neutral charge, right? But they didn't tell me what the other chemical is. Typically they will. In this situation I didn't, but just so you could understand, just add a chemical that's not reactive. Nitrate's your safest bet. Why did I add 2 nitrates? Because a positive 2 and negative 2 gives me 0. That's what I'm shooting for. You have to be 0. My electrons will travel from this side to this side. Why? Because it's always anode to cathode, always. What's over here? We have aluminum, right? And we have Al3 plus floating in solution. How many? Well, 1 nitrate, for every 1 aluminum for each 3 nitrates. Why? Charge is 0 again. It's what you're shooting for. 0, 0, 0. All right, so we're done with the compartments, except we forgot one little piece of detail, the concentration, right? These are all 1 molar. I'm just going to put it, you can put it for each ion individually if you want to. But please remember, in order for this voltage to be valid, this has to be 1 molar for everything. Standard conditions, you have to put the concentration. It's always going to be 1 molar. If it's not, your voltage will be different, and we'll talk about that later. So the last thing is your salt bridge. What are you going to use your salt bridge? Well, if you remember, looking at our choices, sorry, I went too far back. You have sodium chromate and sodium chloride. So sodium chromate, sodium chloride. Which one am I going to use for my salt bridge? Well, can you use sodium chromate? So how do you determine it? Does sodium react with nitrate? Heck no. So sodium is possible. Does chromate react with aluminum or magnesium? Do you see how I did opposites? So chromate's a negative ion, right? So I looked to see if it could react with the 2 positive ions. And the answer is yes, it can. Chromate's, remember, negative 2, negative 3 are typically insoluble. So this is a no-go. Sodium chromate will cause a precipitation. We don't want that. So it's going to be sodium chloride. So where am I going to put everything? Remember, it's anions to the anode, cations to the cathode. So sodium is going to go here, chloride is going to go here. So what happens is that each time magnesium breaks apart into Mg2 plus, you're going to add 2 chlorides in here. So now you're going to have chlorides, magnesium ions, and nitrates. Nothing you can do about that. On this side, you're going to have sodiums, aluminum, ions, and nitrates. Well, aluminum is going to start decreasing over time, right? Eventually, it'll get to 0, but that's not for a while. And that's how you determine how to build a battery. So our overall voltage is 0.7 volts, and these are all the components you need to be able to draw. So if you can't draw this, then that means that there's gaps in your understanding that you need to resolve. All right, here's another one. Draw a galvanic cell using the above reaction, making sure you indicate voltage of cell, the balanced chemical equation, and draw a diagram of the cell, making sure you indicate voltage of the cell, the balanced equation, Okay, so let's do some of it here, because I don't think I made space for it on the next page. Oh, I actually did. Well, let's talk about it first before we start explaining it. All right, so you see this reaction and this reaction both have electrons in the reactants. I need to flip one, right? That's the first thing you want to verify. Do I need to flip? Because sometimes they'll flip it for you just to mess with you. In this case, yeah, I need to flip. Do I want to flip this one, make it a negative number? No. That would be a bad idea. You're going to flip this one. So this one's going to go to become Fe, produces Fe2 plus 2 electrons. Because we flipped it, and because electrons on the product side, this is your anode. This has to be your cathode. That's a lot of chemicals in your cathode, by the way. For those wondering, yeah, you got to put this, and this in your compartment. Why? Because all of them are there. You can't just say, okay, so it's going to be MnO4, permanganate. What about the other 2? They're still there. They can't just go poof. So be aware of that, guys. You don't have to put H2O because it's already there anyways. You don't need to symbolically represent it. So that's my anode, that's my cathode. Now my number of electrons is 5 and 2, so I need to multiply this one by 5, this one by 2. Voltage doesn't change, right? It becomes positive 0.44 volts because I flipped it. But then that's it. These numbers you could already figure out it's going to be 1.95. You don't need to do anything else with the left side to figure that out, because nothing on the left side can impact the right side. So your choices for salt bridge are some hard ones: copper sulfate, sodium hydroxide, potassium nitrate. So we'll see which one makes sense. I'm going to give you an overview right off the bat, just so you have a big picture idea here. Copper sulfide, copper 2 sulfide to be exact, that's insoluble, guys. That can't be a salt bridge, so that's out. So how would you explain it? You would say copper 2 sulfide is insoluble, and thus it cannot act as a salt bridge. End of story. Sodium hydroxide, can it function as a salt bridge? No. Why? Because you were supposed to say hydroxyl form precipitate with the iron as a result, and the manganese. As a result, it cannot function as a salt bridge because it forms a precipitate. That's it. You just got to point out what's going to do wrong. KNO3 would function as a salt bridge because it's soluble in both compartments. That's it. That's how you explain your salt bridge justifications, but you have to explain each one. Please don't say KNO3 is my right answer because it's soluble. Whenever they give you comparisons of different chemicals, you need to talk about each chemical. If you don't, you're going to lose points. Simple math. So don't do it. All right, voltage of cell. Since we want a positive value for voltage in a galvanic cell, we flip the first reaction. We talked about that. So there's your flip. E cell is equal to 0.44. So you could do this in the get-go. You don't need anything else to get the voltage. You can finish it in the first step. The bounce cell reaction is multiply the first one times 5, second one times 2. You notice I didn't need to balance it in that first step to get my voltage. You never do. Just remember, the balance equation doesn't mean anything to you for the voltage. So first times 5, second times 2. And in case you're wondering, what's my N for this? It's going to be the 10 electrons you're canceling out, right? Because both of these are a multiple of 10. That's what you're shooting for. So your N is equal to 10 electrons. If you're doing the change in G equals negative NFE formula, that's what you use. So here's my final reaction. That's wonderful. Remember, the thing you have to pay attention to, this is going to be in my anode compartment. This, and this is going to be in my cathode compartment. But here's the problem you have. You see how the second reaction doesn't have a solid present? That's a problem. You have to have the solid that you can use in your electrode as part of your reaction. If there is no solid in the reaction, you have to use platinum. Why? Because platinum is unreactive, and that's the way we always do it. So anytime, and I mean anytime that you have a half reaction and there is no solid, nothing but ions, use platinum as your electrode. Please remember that. For this one, we could just use iron because we have solid iron there. So if you have the solid, use it. If you don't, platinum's your friend. All right, physical setup of the anode. Since you flip the iron reaction, which has electrons on product side, it is your anode. The electrode that will be used for the anode will be Fe. Electrons travel from the anode to the cathode as always. The concentration of Fe2 plus NO3 is 1 molar. I'll build the battery as soon as I'm done giving you the general synopsis of this. So physical setup of the cell, the reaction with MnO4 is reduction. So we place in the cathode compartment along with Mn2+, along with the H+. Electrode that will be used in the cathode compartment will have to be platinum, since neither MnO4 or Mn2+ can serve as the electrode. Since neither is conducting solid, concentration is all 1 molar. And the salt bridge will have to be KNO3 because of the fact that CuS and NaOH form precipitates. Now, if you're doing it on a test, please make sure you explain for each one individually. Don't do what I did here because of a lack of space. Let's just build this cell real quick so you can see what we're doing. Okay. So you have platinum. So we're gonna go the usual anode compartment on the left that you typically see. So I flip the last one. Let's keep this one as is. So we identify platinum as our electrode in the cathode compartment, and on the left side we say it was Fe. These are horrible drawings, I know. This is Fe2 plus, 2 nitrates to balance it out. So you need the charge to be 0. Here you have MnO4 minus, you have Mn2 plus, you have H plus. So you can have a little flexibility here. You need to make the charge 0, but you could add iron nitrate, or maybe you could add another MnO4. So overall, we're +3, 2 plus 1, and -1 makes it a +2 overall. So we're going to add 2 more MnO4s just to make it a little easier. I'm not going to add nitrate because I don't want to. But the key is your charge is 0. You have your wire connecting your anode to the cathode. So electrons go this way. Salt bridge, KNO3, cations to cathode. So here, anions to anode, here, and that's what ends up happening. So because platinum is an unreactive substance, it's not going to impact anything going on here. So as you get electrons on this side, Mn2 plus, this reaction is going to occur, but we don't worry about that. The only thing you need to understand is that your electrode has to be platinum here and Fe on the left side, and put the ions in the solution, all at 1 molar. Just close the parentheses. That's it. That's all you got to do. That's what the battery would look like for this particular one. All right, important things to remember. Cathode is always where plating occurs, and the electrode will always increase in mass, whether it's galvanic or electrolytic. That's always the case. Cathode is always going to increase in mass. Remember, your goal is to get the highest positive voltage, so you choose which reaction to flip. Based on that, when you're trying to identify the cathode or anode based on giving information, do the following. Look to see which electrode has an increase in mass. That's the cathode. So they give you that hint in the question. There's your cathode, so the other thing has to be the anode. So it's kind of like a process elimination. You're like, okay, well, they told me this. That's my cathode. The other thing has to be my anode. Look to see which electrode has a decrease in mass. That's the anode. They could also tell you that, and that'll help you identify the anode and cathode that way too. Whatever reaction is flipped or is clearly oxidized, which means the electrons are on the product side, an overall reaction is also your anode. All right, free energy and spontaneity. So now that we kind of went over the basics of galvanic cells and Lagrange redox, we're going to talk about how this goes back to thermo. So change in G comes back into the picture. Remember, change G has to be negative for spontaneous reaction, and there's your formula for it for electrochem. So if you have the voltage, you can actually figure out your G. And yes, you can use that same G as you would in thermo. You can figure out your K. And yes, you can use the change G to figure out your S and H if you need to. You can do a whole bunch of stuff. They're all connected. And it's your moles of electrons. Remember the ones you cancel. F is a constant that's in your cheat sheet on the formula sheet. And E, of course, is your voltage. All right, calculate the change in G for the following reaction and determine if it's spontaneous or not. So here's your half reaction. Notice my electrons are already on the product side and the reactant side, so it's already set up. I'm ready to go. Add them together, get my voltage. There's my overall reaction, which they typically ask for. And Fe, 2 moles. Why? Because I canceled 2 moles of electrons. 0.78, because that's my voltage. And what's my G? Joule. And that's the other thing you want to pay attention to. This will give you joules. Always joules. Don't worry about the unit cancellation. I don't want to get caught up with what volt stands for and coulombs. Don't get consumed by the units. You have enough things to understand in this section when having to play unit games. Just understand that at the end of this, you'll get joules. Negative values for spontaneous. All right, so what happens if your concentration is not 1 molar? Nernst equation comes into play. This is the Nernst equation. Good news is, for the AP exam, you don't need to calculate this, but you still need to use the concept to explain why your voltage is going up or down. And I'm sure you how to do that really easily. It's based on what's called your Q. So we're going to ignore all the stuff on the left, and I'm going to base it just on the Q. And if you could do that, you'll be able to figure out the voltage goes up and down based on your concentration. It's really easy. So Q is basically what helps you figure out if the voltage is going to go up or down. Is equal to the concentration of the products over the reactant. So without getting to equilibrium, extreme versions of it, just understand it's a number. How we got the number, don't worry about right now. The only thing you need to understand is that your reaction is going to help you figure out that number. For example, so Q for this one. This is as far as you need to go because you're only going to use it for electrochem. We're going to come back to Q later. But for our purposes right now, the only thing you have to do is real simple. Put the ion on the product side over the ion on the reactant side. So there's typically one of each, right? One on the product side, one on the reactant side. So you're going to put Fe2 plus over Cu2 plus. That's what your Q is going to equal to. So it's going to be based on whatever the number, the concentration of this is over the concentration of this. So for example, they tell you the concentration of Fe2 plus is going up. What's going to happen to your Q? It's going to go up, right? Simple math. As you increase the top number, your number is going to get bigger. Okay, what about as your concentration of C2 plus goes up, what happens to your Q? Goes down, right? Because as this number gets bigger, Q has to get smaller because you're going to be dividing by a bigger and bigger value. That's as far as you need to go with the Q. So they're going to tell you what happens to the concentration of either Fe or Cu. Your job is just to plug it into this equation and ask yourself, is it up or down? So here's the generic way of figuring out Q. It's your proxy or reactants. What this is trying to show you, the little letters are your coefficients. The big letters are your chemical identities. So you're going to raise the chemical to its coefficient. So the coefficient, let's say this was 2, 4, 6, 8. Your coefficients would be 6, 8, 2, and 4. So you would raise it to those powers. That's how it works. So A, B, C, D are initial concentrations. Products are in the numerator, reactants in the denominator. It's kind of like your K. K is also products over reactants. Coefficients in a balanced equation become exponents in the equilibrium expression, like I just showed you. And solids and pure liquids are ignored. So if there's any solids or liquids, you don't write into the expression. That's why I said in the previous example, your ions. The solids are ignored. They don't exist for this equation. So just don't write them in. So here's a question. Write the reaction quotient for the following reaction and determine the value of Q. So my expression for this should be Q equals HI is not a solid or liquid, so I'm going to write it in to the second power. H2, I2, and then just plug and chug. So you're going to plug these numbers in and get an answer, and you should end up with 49. Doing the math. For this one, same thing. You're going to plug and chug. So the only thing you need to ignore in this one is liquid. So that's out. So it's going to be this over this. Sorry, this times this over this. All the exponents are 1 because all the coefficients are 1. So when you do it, you get this, and then plug and chug, you get 2 times 10 to the negative 7. So now that you know how to get the numbers, what the heck do you do with those values? Really easy. If your Q is greater than 1, your voltage goes down. So you see how the Q for this, that 49, is larger than 1? So this is larger than 1. So that means your voltage for this would decrease. So if I were to increase the if I were to use these concentrations for my battery, I would get a lower voltage than what I would get under standard conditions. So your voltage will go down. And for this one, because this is less than 1, your Q, your voltage will go up. So that's how you would explain. You would say, according to the Nernst equation, because my Q is greater than 1, my voltage will decrease. And same thing here. According to the Nernst equation, because my Q is less than 1, my voltage will increase. And that's it. That's all you got to do. You don't have to do any of the scary math. Now, the good news is you're not going to usually have to plug in numbers like this. I'm just showing you how it's calculated, but realistically what's going to happen, one of these will be held at 1 molar, like in the top example. These will both be a 1 molar. And they'll say, okay, what if you make this 2 molar? I know it's a gas, but let's assume it's aqueous for the sake of argument. Then what happens to your voltage? That's all they're going to ask you. So you don't need to do this heavy-duty math even, you have to do it conceptually. So if your Q is greater than 1, the voltage would decrease until you get a positive value for log Q, and thus we'll be subtracting. I won't do the log Q part. I'll just say, according to Nernst equation, because my Q is greater than 1, my voltage would decrease. Done. 100% correct. You could do all the rest stuff if you're really bored, but I won't suggest it. Q is less than 1, voltage will increase into your negative voltage for log of Q, and thus we'll be adding according to that equation. So, very important concept, because anytime the concentration is not 1 molar for a galvanic cell, you have to use this as your argument. Otherwise, you get 0 points. So be aware of it. All right, so explain this equation, write the expression for Q with the correct products and reactant ions, plug in the value for the chemical that is changing while keeping the other one at 1 molar. This is basically set up to do this explanation. So you're going to write the expression for Q, write the correct products and reactant ions, plug in the value is changing, put everything else as 1. Explain whether Q is greater or lower than 1 and whether that increase or decreases the voltage. So if your Q is greater or lower, it's going to impact your voltage. And that's it. That's as far as you need to go. So here's an example. Determine the voltage will increase or decrease for the following situation. All right, under standard conditions, you're 0.48 volts. So that's if everything is 1 molar, right? But look at your Mn2 plus, not 1 molar. So what do? Well, I'm going to follow my steps. Here's my generic expression. I don't need to write this down. I'm just putting it there so you can see it. But this bottom part you do want to write down. So this is a go. So your top number stays the same because it stayed the same. This is 1.5 molar. And without even doing any math, because this number is bigger than 1, I know that's going to cause my Q to be less than 1, right? So if my Q is less than 1, the voltage goes up. That's as far as you need to go to the next equation. So generically, all you have to do is just write the expression based on the ions. So this over this, and then just use logic. You don't have to even get the actual value. You can just say, well, if I put a bigger number on the product side, I'm going to get a bigger Q. Put a bigger number on the reactant side, I'm going to get a smaller Q. Just common sense. If Q is less than 1, voltage increases, and you're done. All right, impact of adding chemicals to galvanic cells. Determine the impact of a chemical. You need to apply the solubility rules and determine whether it will react with anything in the anode cathode. So this is how you determine if you're adding a chemical randomly, like let's add HCl to your compartment for fun. What it's really asking is that, do solubility rules apply here or not? If they do, that's going to change the concentration. So let's look at this example for instance. All right, so what's your oxidation? Is this reaction, right? So this is your anode. You have Al3 plus, and you have Al. Okay, so what if I add sodium sulfide to this? So that means I'm adding Na plus, and I'm adding S2 minus, right? What's going to happen is that this and this are going to precipitate. That's what the question is. That's what's really happening. You have to really use some logic on this. If you add this compound, the sulfide is going to react with aluminum. So what's going to happen to the concentration of aluminum? It's going to decrease. If my concentration of aluminum decreases, then according to this equation down here, if this top number goes down, that means my Q goes down. If my Q goes down, my voltage goes up. That's what it means. So if they are adding a random chemical to your galvanic cell, it's really asking you is that will the concentration of any of these chemicals change because of it? And it's going to be based on solubility rules, guys. So just make sure you think about solubility rules when you think about adding chemicals to a situation. If an added chemical forms a precipitate with something in the compartments, then this concentration of that particular substance will go down. Nernst equation needs to be applied. So when they're adding chemicals to your galvanic cell, it's a Nernst equation scenario based on solubility rules. So you see the combos coming out of nowhere? It's beautiful, I know. All right, last thing we're talking about is electrolysis. When electrical energy is used to cause a non-spontaneous reaction to occur. That's what electrolysis is. Example, current of 0.452 amps is passed. So you could tell electrolysis question because amps and time are given out of nowhere. In the following scenario, calculate how many grams of chlorine. So they're trying to figure out grams of chlorine from this. I'm going to give you a shortcut to do this. It's unlikely to show up on the AP exam. It typically doesn't, but just in case it does, all you need to do is remember this. What's that? Moles are totally awesome forever. And I know deep down you feel that way. You know, deep in your heart, you're like, moles are totally awesome. They'll be like that forever. You're absolutely correct. So by remembering that little fact, you can basically set up the formula. So the totally awesome is time in seconds, A in amps. The forever part is Faraday constant, which is 96,500, and the moles of electrons. Remember the same one we used for N, for the NFE formula? Same one comes back into play. So let's take a look at this. Moles are totally awesome forever. So for moles of Cl2, there's a totally awesome part. I changed the time to seconds. Amps they gave me, I kept it, 96,500. This is the same thing as 96,485. It's just, it's rounded, and it's fine if you round it, don't worry about it. Your moles of electrons, 2. Why 2? Because if you look at your original reaction, 2. That's why. And there's your moles. Now, if you want to get your grams, multiply by the molar mass, and you're done. Beautiful, right? By the way, they give you something like, say copper nitrate to mess with you. Say, oh, hey, what if you have copper nitrate? And how many grams of copper would you produce? To figure out the charge or number of electrons, just based on the charge. This is a positive 2 charge, so you have 2 electrons. If I have FeNO3, how many grams of iron will you produce? Oh, sorry, this is 3. Your charge is positive 3, so guess what? 3 electrons. So what I'm telling you, shortcut is that you can figure out the moles of electrons based on the charge of the cation. It just works. So just an idea. All right, so here's a question for you. You have a galvanic cell by looks of it, because your voltage for the reaction above, Okay, so I guess we have to figure out if it's galvanic or not. We're going to have to assume it is because there's nothing contradicting it, or do we? No, don't assume. Remember what I told you, don't ever assume. Base it on the data. So how do I base it on the data? They give you a balanced reaction. Fe is the one being oxidized. So guess what? The one you have to flip is the one where Fe. So you need oxidation for everything. Look what they did to you. They already put it on the product. See how brutal these people are? They made both these oxidation reactions just to mess with you. Why? Because they can. So what do you have to do? This reaction is oxidation, so I'm going to keep it as is. Electrons in a process, what I want. Because identify as oxidation. That's what I mean by use the data. Don't assume. So what is Br2? It's going from a 0 to a -1. That's reduction. So I need this one flipped. And when I flip it, the voltage is also flipped. See how brutal that is? I mean, if you looked at this and you didn't know that, you're dead in the water. But that's how you would do it. So you could do it that way and figure it out. But that's not the first thing they're asking. They're asking for S. So thermal and galvanic are going to be hand in hand. Electrochem are going to be hand in hand. So how do we get our S? Cross minus reactants, right? So you have the overall reaction. You have the coefficients. Do the math, the setup. So 2 times 19.6, 2 times 90.2. I just did products minus the 2 reactants. Calories, I really don't care about the units, but that's what they gave you. So negative 105.4 calories per Kelvin. I'm going to change it to joules at the end because I know I'm going to need to be in joules. The good news is they don't really do the whole calorie thing anymore in the AP exam. I just throw it in there because it's fun. And it kind of reminds you of that whole 4.18 conversion, but on the AP exam, don't worry about it. So this is your change in S. So based on this, is it spontaneous or non-spontaneous? Well, if you look at it, it's a negative S, right? So negative S is bad because it makes your G positive. So based on this so far, we're going to say the reaction doesn't want to occur. We don't have all our data yet, but it's that kind of thinking you need to start incorporating in your head, right? Entropy is negative. That means it's not spontaneous from entropy's point of view. It also means this is going to work better at low temperatures and high temperatures because the low temperatures, the T change in S formula is going to give you a smaller value, which is going to be less positive. That's the kind of stuff you want to start floating in your head. All right, so your G, negative NFE. Why is it 2? Because you have to multiply the second reaction by 2 to cancel it out, right? Your voltage is 0.30. Why 0.30? Well, when you flip this first reaction, it becomes 1.07 minus 0.77, and that's where you get the 0.30. So you have to know that. And if you didn't know, as far as looking at where the electrons are to determine if it's oxidation reduction, if you didn't know that the final reaction gives you all that data, this question becomes impossible. So the devil's in the details in this section, guys. Pay attention to the details. So change in G is equal to negative 57,900. And now they're doing H. Awesome, huh? You got S, you got G, you got your old friend H back in the mix. Just when you thought you had said bye to it for a while, it's coming back. So we're going to write the equation, solve for H, plug and chug, there's our H. So remember, there has to be a driving force for this reaction, right? Your S was negative, it cannot be the driving force. So before you even started, you should have been like, wait, this reaction occurred, right? Okay, G has to be negative. So what does H have to be based on that? Negative, because the only thing that can make your G negative if your S is not going to be the driving force. That's the kind of stuff you need to start thinking about. That's when the big picture starts developing in your head and you start seeing the connection between ideas. That's what gets more interesting too. Much more interesting. All right, here's another question. Electrochemical cell consists of a tin electrode in an acidic solution of 1 molar SN connected by a salt bridge. Second compartment with a silver electrode in acidic solution. It's more active. Write the equation for the half fraction occurring in each electrode, indicate which half fraction is at the anode. So you have your N, you have your silver. All right, so how do we know which one's which? All right, so it consists of a tin electrode in acidic solution, 1 molar SN, connected by solvent. The second compartment with a silver electrode in acidic solution. Tin is more active. There's your magical words. So tin is more active, which means the word active, in case you didn't realize, means it's higher in the electron potential chart. So SN is here, silver is down here somewhere. So by telling you it's more active, they're telling you it's higher up. So it means that, remember, the thing that's higher up wants to do whatever it is you want to do. But for reduction potential, the higher up is usually the one that wants to get reduced, right? Okay, that's the one thing that you have to walk away from for this stuff. When they use activity series, and you could go look in activity series, but that's going to confuse you a little bit. For activity series, the higher up it is, the more it wants to get oxidized. So when the word activity is used, active, it's not going to be reduction potential chart like you're used to. It's based on something a little different. So this is oxidized, this is reduced. So when they're doing metals and it's activity, the higher up one wants to get oxidized more. That's all you need to know for now. The one that's higher up wants to get oxidized. So the more active means wants to get oxidized. All right, so write a balanced equation. So I got my numbers for the reduction potential chart. I set it up. Now I need to do some flipping. So you have Ag plus going to Ag, and this should have been a negative. So it's a positive number. Yeah. So the higher up it is, the more it wants to get oxidized. But in this situation, you can see that what's happening is that I gave you reduction potentials, and I should have showed you what's happening next. Let me do that real quick. So you have Sn produces Sn2 plus 2 electrons. We identified it's more active and wants to get oxidized. So this goes from a negative 0.14 to a positive 0.14 volts. So then it's 80 plus 0.14. That's where you get this from. And now you have your electrons on opposite sides, which is what I need in order to do this scenario. Because if they're on the same side, it doesn't work. So your voltage is going to be 0.80 plus 0.14. Checks out. My final reaction is going to be 2Ag plus Sn. Notice Ag is being reduced like I projected it to be. This is oxidized like I expected it to be. So a little tougher question, but I just wanted you to be familiar with oxidized. So if you excuse me, with the word active, so if you see the word active, just remember the one that's more active wants to get oxidized. Just take that away and nothing else. I don't want to get you consumed by activity series and do a whole bunch of other analysis. Just keep it simple for now. All right, calculate the equilibrium constant for the cell reaction at 298. There's your formula. There's your K. Plug and chug, 6.47. It was spontaneous, right? Your G was negative, so you expect your K to be greater than 1. It's really, really bigger than 1. All right, cells similar to the one described above is constricted with solutions that have an initial concentration of 1 molar and 0.2 molar. Determine what happens. So there's our equation. Remember, put Sn2 plus over Ag plus. So I'm going to do that real quick. So Sn2 plus Q equals Sn2 plus brackets, because brackets mean concentration of Ag plus squared, because there's 2 of them. So your Sn stays 1.0 molar and 0.2 molar for this. So I don't even need to square the number. Because the concentration of Ag is less than what it used to be, remember it's supposed to be 111. By decreasing the concentration of Ag, whether you square it or not doesn't matter. Your Q is going to be greater than 1. Right, guaranteed. Your Q is going up. So because it's above 1, then the voltage is going to decrease. It's the opposite relationship, as we've said many times. And that's electrochem.